Do, do. Oh, hey, we're live. We're on the internet. Hey, everybody! Welcome once again to another Rust Meetup. Thank you all so much for coming. This month we have the Rust birthday, and Frank McSherry flew in all the way from Europe to talk about timely data flow. As always, thank you so much, Mozilla, for feeding us. There is lots of pizza and lots of cake, so anyone on the internet, if you want to get here in less than an hour, feel free. But before we actually get into the festivities, I think that's how you say it, I wanted to at least do a call out that we are doing a survey of the Rust community and also the not Rust community, but is potentially interested in it. Here are some links on how to actually get to the survey itself. You can actually just go to blog.rustlang.org and fill it out. It should take about 5-10 minutes. It would be really helpful, and it would help us figure out where to take Rust over the next couple years. So this is going to be an annual tradition. Anyway, we have birthdays. So first off, Aaron wanted to talk about, Nico and Aaron. Someone is going to talk about birthday stuff. So please give them a warm welcome.
Thanks, Eric. Hey, everybody. Thanks for coming out to celebrate Rust's first birthday. So we're going to have an anniversary blog post coming out on Monday, but I thought I would give everybody a preview of some of the highlights, just to sort of look back at what's happened this year in Rust. So first of all, we've had some people gathering some numbers, so this is mostly thanks to Hugh and Wilson, on just what has happened numerically in Rust in the past year. So we've had almost 12,000 commits by 702 contributors to the core Rust repository. So this is not counting the many other libraries that live under the rustlang organization. And this is particularly encouraging, right? So we had over 1,000 contributors prior to 1.0, and there was some worry that maybe this was sort of the hype around 1.0, but actually people are still contributing a year after in almost the same volume we got all the way up to the beginning of 1.0. That's extremely encouraging. We merged 88 RFCs. We introduced 18 new compiler targets and shipped 10 releases, and of course delivered 1 year of Rust that does not break the way that we were doing before 1.0. Now, I want to say one other thing, so I didn't put this on the slide. So those 88 RFCs merged, so that's an average of almost 2 RFCs a week, which is a pretty aggressive evolution story. And there are some other interesting figures in terms of crate publications. So not a single day has gone by in the past year that somebody hasn't published a new Rust crate. Every single day, someone is publishing a brand new library in Rust. And in fact, most weeks, we get about 53 brand new crates. Not new versions of crates, new crates. I think that's incredible. This community continues to blow me away every day. Okay, so those are some numbers. There's one more number. This was probably my personal favorite number of the year. So Stack Overflow, did their usual annual survey of developers, and one of the things they measure is sort of how do people feel about the platforms that they're developing with. So this is, if you're developing with a language, how much do you want to continue developing with it? And not only is Rust on top, but it's on top by a significant margin. And I feel the love. This is amazing. And I think if you're active in the Rust community, you can feel this too. We all have a lot of affection for the project. It makes it really fun to be involved. Okay, we are also starting to see Rust cropping up more and more in production. So Brian Anderson has been working on this amazing page with Friends of Rust, where people can submit logos of their organizations if they're betting on Rust in some way. So they're using Rust in production, prototyping things with Rust, whatever. Somehow they're putting some money behind Rust. So there are a lot of stories here and a lot more icons than I can show on this screen. But I wanted to talk about a couple of the biggest stories of the year. So one probably a lot of you heard about because it was featured in a big Wired article is Dropbox. So Dropbox is using Rust in production today in a pretty big way. So over the past 2.5 years or so, they've been moving away from Amazon's web services toward their own storage backend. So they've developed new server architectures and an entirely new sort of backend software stack to manage them. A lot of that software is written in Go, which has been the traditional sort of Dropbox backend story, but there were some core pieces for managing the data on these servers where Go was just using too much memory, and there was no way that they could sort of get the footprint down where they needed it to be. And so they turned to Rust, and they've been extremely happy. The core team has been in touch with them regularly, asking them, what do you need? And their answer is always faster compiles. But otherwise, they're pretty happy. I think that's been one of the most encouraging success stories. That's a pretty big bet for a pretty big company to make on Rust. And I'm sure that we'll see a lot more following in the years to come. Of course, I would be remiss not to mention Mozilla, another fairly big company betting on Rust. Of course, most of you have heard about the Servo project, which is sort of the sister project to Rust, a new research browser engine. But that's not actually the story I want to tell today. So as of some weeks ago, I'm not sure exactly when it shipped, Firefox is shipping Rust code in production on Linux and OS X. It'll start shipping in Windows in a few more months. Now, we're taking things in a somewhat conservative fashion, right? So the way that this is starting out is we have a C++ component, and then we have a Rust component that's doing the same thing alongside. And sort of minority report style, we're asking both what they think the answer is and reporting any time that the Rust component gets it wrong. Well, I'm glad to say in almost 1 billion recorded runs that have been sent up by telemetry, Rust has a 100% success rate and has caused 0 crashes. Yeah. Now, this component is an MP4 demuxer. It's just one place to get started. But I can tell you the sense inside Mozilla is a lot of teams are chomping at the bit to start rolling out Rust inside of Gecko. And so we've been waiting to sort of see it proved out, get it integrated into the build system. But this year, you can expect to see a lot more big news in Gecko coming out of Rust.
That team is very proud to be the first team to put Rust in the 5.0.
Yep. All right, Nico.
All right. So that was kind of what's happened over the last year, and now we're going to talk a little bit about what's coming up in the near future. So first off, we have a lot of meetups going on. You can see here all over the world, basically. And I think a number of them are also having special events right around now. But after that, we have a couple of conferences coming up. So one is RustConf, and it's going to be in September in Portland. So that's kind of for the West Coast people, which I guess is the local audience. But if you're on the East Coast, like myself, you might be interested, or even if you're on the West Coast, in Rust Belt Rust, which is coming out of the Rust Belt in Pittsburgh. And that's going to be October 27th and 28th. And I think they're accepting or not yet. People.
Yeah, it's already done.
The CFP is closed, but I'm not sure if you can register yet. But
no, I don't think.
Hopefully soon. Yeah. And finally, we don't have a lot of details, but we can say that there will be something in Berlin and around a similar time frame, and hopefully that'll be announced in the next few days, and maybe some other European events as well. So you should definitely attend some of those. It's going to be very interesting. And that's about all we have to say. But, we love Rust. We hope you love Rust. Thanks for being here.
Happy birthday!
All right, next up we have Frank McSherry. But I have to say, first off, it's super cool that there's an actual infant here. So I think you have to bring your kid to every future event so that we can track, their progress. So anyway, Frank McSherry.
Hello, folks. Thank you, Eric. I'm out here for other things, but Eric has been trying to get me to give a talk for a while, and I'm delighted to be here. And I didn't realize it was a big celebration. There was cake for me and everything. It's so sweet. And I'm going back to Berlin, actually, at the end of the week, and I'll go to their happy celebrating event and probably eat some cake there, too. And life is good, beer. So I'm going to tell you about timely data flow in Rust. This is a project that I've been working on. I've been playing with Rust for about the past year and a half or so. Pretty stable stuff where I picked it up mostly by chance. I told some friends I was going to learn Go, and they said, "Oh, you're stupid." And so I felt embarrassed, and so I picked up Rust instead. And it turned out, like, you couldn't have told at the time, but it turned out that it was a very good choice. I'm delighted. I'm one of those 79% or whatever who are going to keep doing this for a little while. Timely data flow in Rust is, you'll see it's a collection of some things that I've been working on that's built on a bunch of work that I've done in the past with several other people. I want to put their names up here because they're important. These are people who were at Microsoft when I was working there, Microsoft's research, and also at ETH in Zurich, where I had been relatively recently, up until about January or so. You can find stuff about me on GitHub. I'm delightfully unaffiliated at the moment, which makes me very happy. So I don't actually have a proper homepage or anything like that, but I have GitHub, and you can find lots of things that I do there. Yeah.
Slide over a little bit to talk. Yes.
Is that? I'm sorry.
Yeah.
This is. I'm now in screen. Okay. Cool. So the talk is going to be primarily about large-scale computation, doing it in Rust, how Rust in particular has made my life a lot easier working with big data and big computation. It's a little bit of a weird talk because it's going to hit a few things that are interesting and new in big data computation, but it's also going to try to touch on, if you're keen about Rust and trying to figure out, is it a good idea, bad idea, the moments that I've had where I've had some pretty good experiences and done things differently than I have in the past because of Rust, and have felt eventually smarter and better for it after a little bit of mortal combat with the various components of the Rust system. So let me start with some fun numbers that I like to just motivate where I am and why I do things. These are some numbers for some big data computation. They're a little old at this point. They're stale. I'll get some more fresh numbers towards the end of the talk. But it's a paper on graph processing, and there's a bunch of exciting popular systems for doing PageRank, in this case 20 iterations of PageRank on a few different data sets on lots of cores. This is a cluster of, in this case, 16 machines grinding away and doing some things in hundreds of seconds. And it's pretty exciting. No one had a great sense of whether these are brilliant numbers or not, but they thought, sure, they look good. And we, sort of difficult people, went and I sort of pulled out my laptop, which is somewhere up there. Please don't run away with it. That you can write fairly simple things. This code happened to be in Rust that I wrote, but it actually works similarly in C#. We also did it in that. But with a little bit of care and attention, you can get relatively good performance numbers without all of the exotic parallelism big data systems, which was a little surprising. I mean, these scalable systems seem to have a lot of gunk sort of built into them that makes things go slow. And these are the people we went to try to actually get the computations that were too hard to manage to go excellently, and in these particular cases at least, they didn't really go any faster than our laptops. So that was a little bit of a surprise, and for a while we were quite smug. We were like, look how clever we are. At which point people started to say things like, maybe you could stop being so obnoxious and start to be helpful. And that's sort of what I'm going to tell you about in this talk, which is a system that takes some of the similar ideas, just like attention to detail, basically. It's going to be in Rust, but to be honest, it doesn't have to have been in Rust. Rust just happened to make my life delightful when I did this, and I'm very happy when I use Rust. And that was the only way this is going to come into existence anyhow. So we're going to talk through some of these things. Actually, the next slide is a stack picture. So we have some parts of the talk. There's going to be timely data flow, which I'll tell you a bit about. It's a few things. It's a Rust crate that you can go and grab, but its role in life is sort of something a bit like an operating system or a runtime for data parallel computations, and we'll walk through a bunch of examples. It's built on top of a bunch of fun parts, also crates that you can go and pull down if you want. There's this serialization crate that I like a lot. I don't think I'll have the time to tell you all of the exotic details about it, but it's basically how to serialize data very, very quickly at the expense of a few inappropriate uses of the unsafe keyword. Anyhow. On top of the stack, though, as we go up, you can take these core primitives for data parallel computation and build some languages or frameworks on top of them that are a bit more like analytics languages. They're a bit more user-facing, a bit more friendly, and have a bit more magic built into them and do some pretty cool things. So I'll show you one of those, differential data flow, which is essentially a collection-oriented programming language that magically updates in real time and does a few things that previous systems just haven't been able to do that I think is pretty cool. And you can put on top of these neat applications hopefully we'll get to a few examples of these towards the end. And I've drawn the picture this way so that you can see that they, because of the way we've layered things, they touch down wherever you'd like. If you want to write stuff against core timely data flows, great. That's delightful. If you want to write stuff against various higher level libraries built on top of it, that's also delightful. They all sort of compile down to the same thing, so you can pick and choose what you want to use. And hopefully that's very exciting and appealing to well, to people who want to use the good, the prefabricated stuff when it's appropriate, and when they really need to get in there and change bits and pieces, that's open too. So I'm going to start just with the timely data flow stuff, the delightful Keynote animations. If anyone hasn't used those, they're so nice. If people have questions at any point, especially clarifying questions, if I've said something that's confusing or you don't entirely understand, feel free to ask. I'm going to be here after the talk, so if there's like deeper dives you want to take into things, maybe you hold on to those. But if at any point I've said something that seems weird, it probably seems weird to other people too. So feel more than welcome to jump up and down and make me say it again, maybe with different words. So this is based off of some work we did in SOSP in 2013, but there are some fundamental changes that went on when this was ported over to Rust, mostly because we couldn't write the code the same way. But it was all for the best, as it turns out. Things became better because Rust made me a better person. It pointed out all of the places where I did something totally inappropriate, and I had to fix that. And now I'm anyway. So timely data flow. I'm going to walk through a very simple example. It is a crate and such for doing data parallel programming. So what's going to happen in the fullness of time is you're going to write a program that's going to get spun up on potentially many different computers. You can do it just on one if you like, of course. But I thought I would walk through the different levels of parallelism that exist in one of these computations, just to sort of show you a little bit about how we think when we write one of these programs. This is basically the shortest sort of hello world style program you could write, and it's going to print some numbers to the screen, basically. First off, there's your program. Now, your program is the whole thing. You write this once. Even though you're going to run it a few times on a few different computers, there's one hunk of code that you have to think about and put together that actually gets run. You don't write the program differently if you have a different set of machines. You don't have to write different programs for each of the different machines. So there's just one program, you and your laptop or wherever you enter code into, that gets written once. There's this block within sort of the main region, which, so as you might expect, is the per process logic. Each time you spin up one of these computations on a machine, maybe this is only once because you're just doing it on your laptop, this is going to get run. And this isn't the most exciting part. This typically just calls into timely and says, hey, I'd like to participate in a big parallel data flow computation. Can we do that? But I did want to point it out here. There's very rarely in the examples I write code outside of this region, but it's totally possible. Most of the excitement goes on in this inner little bit of code here. This is inside this closure that gets passed into timely. And this is the per worker logic. So there are lots of people, lots of threads that are going to participate in some computation, and this is the point of our program when we tell them, what should you do? What should you want to help out with this big data parallel computation? What should each of you go and do? And it's just going to be Rust code, right? So nothing particularly exotic. We're not writing a different language or anything like that. But yeah, let's walk through what this example does. For example, so it's Rust code. We start in this case just with a Rust iterator. If you've seen these before, great. I'm a little. How many people are absolutely brand new to Rust? Never seen it before. Okay. I'm going to try not to lose you. Yeah, but I'm going to screw it up. So, at this moment, we're just running computation, random bits of Rust code that we can write whatever we want, and we're going to start with just a Rust iterator. 0 dot up to 10 is 0 through 9. It's just a little bit of code that returns some data. Nothing magical about that yet. No fancy distributed anything yet. Though there are methods exposed by Timely through the data flow operators space that let you convert things like Rust iterators into distributed streams or collections. In particular, this toStream operator takes this scope, which is basically a handle to the data parallel runtime, and says, you know what I'd really like to do is I'd like to take this data that I have here and convert it into a distributed pile of data, a distributed stream I've written. And it's still conceptually 0 up through 9 on each of the independent workers. Though now all of the workers know that it has a name, all the other workers know about it. It's sort of a shared pile of data that we can start to interact with. In particular, for example, we can do something like a data exchange. So we have a bunch of workers. Let's imagine, hypothetically, 5 workers out there who are each thinking about the numbers 0 up through 9. And we've just told them to take the numbers 0 through 9 and make them into some potentially distributed collection of data. They did that. They're each sitting now on the numbers 0 through 9, and they're not really sure what to do with them yet, but they know that there are 4 other people who have a similar pile of data. The exchange operator is going to tell them, now, next thing you should do is shuffle all this data around between all of you. This is a fairly common pattern in a lot of these big data systems, right? A lot of them work by describing what individuals should do, individual workers should do, and how you should move data around between the individual workers. What the exchange operator here does is allows you to say, for each record that flows by, if you show me the record, I'll tell you a number, as it turns out. And the number is going to drive which worker should I route this particular piece of data to. So we're going to send all the zeros, for example, to the same worker, worker 0. All of the ones are going to go to the same worker, et cetera, et cetera. We'll wrap around at 5, that'll go back to 0 in the case of 5 workers. But this is basically how do you take a distributed collection of data, many copies of 0 up through 9, and shuffle them around between all the workers. Now we have a distributed collection of data, and the data are in different places than where they started out. So that's sort of this is, again, it's a hello world example. Hopefully you're not too excited about this. You haven't gotten your checkbooks out yet. But we've moved some data around, and we're now going to do a thing, is inspect, which we try to borrow as often as possible iterator idioms from Rust so that you have the same sorts of vibe when you're working with iterators as you have with these distributed streams. But this is the same sort of thing. Every record that goes by, it'll just call some Rust code. In this case, we're going to print something to the screen. But rather than have each of the workers print 0 through 9, worker 0 is going to print a whole bunch of zeros, maybe then a whole bunch of 5s, 1s and 6s, that sort of thing. So we've caused the data to move around a little bit and do something different on each of the workers than it would have done if we hadn't actually had a distributed computation with communication. So super primitive, sort of hello world style example. Yeah, shoot.
So each one of the workers is producing
I can repeat the question if that's. Oh, there's a mic.
So each one of the workers is producing its own stream from 0 to 9?
Yes, in this case, absolutely. Each worker is going to hit this code here, and often this is a bit of a silly example in that each worker does the same thing. That's sort of dumb. A smarter thing would be for the worker to grab its index out of the scope object, which it has access to, and say, based on who I am, maybe I should do something different, like potentially pull out 0 through 10, but only those folks who have the mod equal to my index when taken mod number of workers. Yeah. Bad example, but so we're gonna do something great. Let's do something more exciting then. That's a good point. So we're gonna do something a little bit more exciting now. The font is a little smaller. I hope it's still readable in here. I'm going to show a bit more of an exciting example now. The previous one was basically a batch computation. It was there's a pile of data, it exists, and we act on it, which is cool. A lot of people like to do that sort of thing, but it's not really a data stream yet. We're not feeding data into it and seeing cool stuff come out the other end or anything fun like that. We're just going and we're done and the program ends. So let's write something that's a bit more interactive. And it's pretty similar. I feel very bad about lying on my slides about code, so the timely examples thing doesn't technically apply anymore, so I had to change it. But timely execute from args is the right thing to call to run this example. We start out with a little hunk of code that's very similar in spirit to the previous hunk of code. Rather than just announce the numbers 0 through 9, we're going to create an input which has the goal in life that it can be turned into a stream on the one hand, but it also lives on, and we can feed data into it interactively in just a moment. With that input, we're going to, and bear with me for just a moment, in the context of some method that I haven't explained yet, we're going to turn it into a stream, we're going to do this exchange, we're going to print some stuff, and then we are going to call the probe method on the end, and that's, okay. Who knows why we did that? I'll try to explain. The timely part of timely data flow is about attaching logical notions of time to the bits of data that we have in our hands. When we just had this batch computation, we had some data just existed. There wasn't really a notion of time. It's just there. What we'd like to do is create a new scope to work with data in which the data have an interesting notion, a non-trivial notion of time. For example, in this case, we're going to have unsigned integers that go up from 0 to, well, it's going to be 10, it turns out, but could go on indefinitely as we interact with the data flow. So the scoped operation basically builds a little bit of our data flow canvas that we're going to work within, where inside this canvas, all of the data that circulate around have some notion of time associated with them, this unsigned integer that is going to correspond to rounds of input. The probe operator is a little bit of sort of a dual here, where it lives on the end of the data flow and is the thing that can tell us how much progress have we actually made through this stream. Great, you're talking about zeros and ones and twos with respect to your timestamps. Have we seen all the zeros yet? Have we seen all the ones? Have we seen all the twos? And this will be the little handle that we look at and say, how much progress have we made? Have we finished all of a particular piece of the computation? Data flow is a little different than imperative programming in that you don't get to point at a particular line of code and say, do this right now. You set up a computation, you wait for the data to arrive, and once the data have arrived, computation happens. But you, as an individual worker, don't really control when that happens. Someone else might be sending you the data, and you don't get to force it to happen now, but you can hang around and sort of chill out until it happens, and that's how we're going to use the probe operator. So just to finish up the example, there's a second, having built up the little bit of data flow that we're going to work with, there's a second hunk of computation where we drive it. Basically, we take the input and we take the probe, and in this case, we're going to go through the numbers again, 0 up through 10. We're going to do a few things. We're going to feed the current round into the input, so everyone's going to stuff a 0 into the input and sort of introduces a 0, as it turns out, at time 0. The input gets advanced, and what that means is that it moves the timestamp forward to 1, and that's a very important action to take. That tells everyone else in the system that this worker is no longer planning on sending anything that has a 0 timestamp on it, which is very helpful because now all the other workers, if they're listening, can say, oh, good. If we finish all of those messages that you sent and they get out of the system, we can comfortably decide collectively that we're done with that round of computation. We can announce to whoever's interested that we've made some progress and we're good to go. Which is actually what we do in this third step here, is we basically tell the worker, why don't you keep running for a little while? In fact, keep running until that it's no longer the case that that probe thing you're looking at is strictly less than the current input time. So as long as you're at 0, which is strictly less than 1, keep going. And when we move on to the next time, as long as we're still at 1, which is strictly less than 2, keep going. This will drop out as soon as we're ready to move on to the next epoch, essentially.
Step while does multiple things?
Yeah, step while is sorry. So the question is, what does step while do? So the way Timely is rigged, at least, step while you can think of as there's a step function which takes no arguments, and that's basically schedule everyone in the data flow once. Go through all the people who could do some work, the exchange operator, the inspect operator. We'll see in the very next slide what it is they might do, but give them a chance to do a little bit of work to look at some data, and then come back. That might not have finished everything. So step while is just a helpful little function that says as long as this predicate evaluates to true, just keep doing that.
So it's one time through the body or the other thing?
It's as many times through the body as it takes to get all the work done in this case. Sorry, this probe less than input.time will become false once all of the data for epoch 0 have flowed through the graph. Maybe there's some other worker you've set up on some foreign continent who's taking quite a while to get the data to you. You'll hang around. You might go through this loop a bunch of times saying, I'm working, but I'm not seeing anything. I'm working. Eventually the data will show up, or some message will show up announcing, we're good. We've seen the last of the zeros. Feel free to move along. Yeah, please.
So inspect, it runs the code from random computer.
So the question is, I think, where does inspect run the actual code? And the way it's going to work is each worker is going to have a copy of inspect. So every worker, if there are 10 workers out there, there are going to be 10 copies of inspect, and they're going to be driven by what data they actually receive. So if you send all the data to one worker, only one worker is actually going to do that particular work. If you spray the data across many workers, many different people will do the work. But it's driven by how you distribute the data as opposed to trying to place a particular worker on a particular machine. Yeah. Cool. Okay. There's a question. No. No. It's good? Okay. No, sorry, it's not good. I'll carry on. I'm sorry. Again, feel free to grab me. Or if you're actually, seriously, like if there's an issue, jump up and down and I'll keep going until there's more jumping. So I did want to point out that this, maybe I called this up a little bit, but this is a very exciting moment in terms of timely data flow. This little bit of probe less than input.time. This is the moment where, although we've written a little bit of local code, this is local thread running and saying, what's going on here with the probe and the input. This is where we take information about the distributed state of the computation. So things that might be true on other machines, other workers, wherever they happen to be. And we get information back that helps us make a local decision about should we keep doing a thing or not. So this is where a lot of the magic is hidden with respect to timely data flow. The thing that it does that's pretty cool is let you write interesting data flow graphs and give you information about are we there yet or not at any particular point in the data flow graph. And that information can drive a lot of fairly useful computation. Yeah, there's a question.
Yeah, so the probe's not only sending a message to all the workers and getting back their states.
So the question is, what is probe actually doing? And the answer is actually, it's a lot more passive than that. Probe is just sort of chilling out. There's some background coordination traffic that's going on. Basically, each of these workers are listening to exhaust from each of the other workers about what they've done. And when you ask the probe what's going on, the probe just sort of says, well, as far as I'm aware, no, we're not done yet. And it doesn't do anything particularly active in terms of issuing queries to other workers and harvesting stuff back in.
The callback return.
This will return immediately. It doesn't block or anything like that. It'll return and tell you according to the current state of information whether they're done or not done. But it doesn't block or anything like that. Almost all of timely data flow everywhere is non-blocking. It's sort of by design in a data flow system. You don't really know if you can actually do some work or not, so it's great not to block, assuming that you can. Just a design goal throughout. So if you've used streaming systems before, you might know I can do all of this. This is not particularly new. There are lots of systems out there that let you do this. So let me show you something that's new, that's cool, or I think it's cool anyhow. We'll get rid of that silly exchange and inspect thing and put in some more exotic computation. We're going to throw in that stream of numbers they get fed in, and we're going to feed them into an iterative subcomputation. So we're going to say, take those numbers and do the following. Until we run out of data, I guess. I mean, this is what iterate means. Take the data, hit it with this filter that keeps only strictly positive elements, subtract 1, and then do a little bit of exchange. Which, if you think about it, is going to take some numbers like 1 million. You put 1 million in, and it's going to count down from 1 million down to 0. And each time it counts down, it's going to do an exchange and probably hand it to a different worker. And essentially, we're getting a little data exchange micro benchmark going on here. And there's a few things that are cool. One of the things that's cool is that this actually still works. That you can still get information, that probe still comes back and tells you, yeah, we're done or not. And you might say, oh, that's a big deal. Naiad and Timely Data Flow and Rust were the first systems that were able to do this correctly, basically. It's really hard. The reasoning mechanisms people had used before had a really hard time breaking out of loops, basically. If you were in the loop, you could tell what iteration you were on, but it was really hard to have a computation that would spin for a little while and then tell you, yeah, I'm done, let's go on to the next one. The other cool thing is, so I mentioned this exchange microbenchmark, it goes pretty fast. So you can spin around this thing if you're actually trying to figure out how fast does it go. Depending on what sort of rig you use, so if you just have one thread, things are pretty fast because you're just pushing and popping on a queue. 2 threads, pushing and popping on a channel. And as soon as you start to involve multiple processes, you do have to bounce in and out of the kernel because it's using this vanilla TCP, but you're still in the tens of microseconds regime. And by comparison, if you've used other systems, big data systems that try to do iterative computation, the startup costs associated with going and doing a computation is in the typically hundreds of milliseconds at least space. So it's cool. There's some potential. We can move data around pretty quickly. Let's see what we can do with that. We'll see. Sorry, in maybe tens of slides what we can do with that. Yeah, shoot.
So, just to make sure I understand what's happening here. What's happening is you start out with a certain set of data, let's say 0 to 10. Then you map each one down, so you get -1 to 9. And then do some exchanges, and then feed that back in, which then gets filtered, and that's why erasers are fixed.
So in this case, actually, the code as written, this is great, actually. It's a brilliant segue into the very next minor transition. The code as written, what will happen is 0 will go in. From each of the workers, 0 will get thrown away. They will drop out and say, hey, are we done? And the computation says, yeah, we're done. Apparently, everyone threw away their zeros. Everyone will then stick in a 1. The 1 will at least survive 1 iteration. That's not very exciting, but it survives 1. Everyone dumps all of their zeros basically onto worker 0, who then throws them all away. And as we go up, each worker introduces some number between up to 10. All of them get dumped to the same worker who picks them all up and dumps them to another worker, and picks them all up, dumps them to another worker. But they're done in sequence. Everyone does zeros, then they sort of block while everyone agrees that we're done with all the zeros, then they move to the 1s, and they move to the 2s. So there's a very strict, in this case, serialization going on, though, you can, like I mentioned before, this is a totally passive operation, this probe. So it doesn't actually block the computation until something is done. It just tells you what the current state of affairs is. And if you'd like to build in a bit of slack, for example, because it's productive to have concurrent bits of data cycling around, you can totally do it. This example says, hey, if we're within 2 of the current time, let's keep things going, which means that we can have, in this case, 3 outstanding rounds of data circulating at the same time, and it's a productive way to keep more of your CPUs occupied. I mean, this particular example is a bit silly just to begin with, but this principle generally, let's keep a few outstanding epochs going at the same time, is a fairly helpful way to get higher throughput out of a streaming system at the expense of a little bit of latency, if that matters to you. But cool. Yeah, and the point here, I guess, is meant to be that this probe operator, and the concept generally, the concept is promoted to a first-class concept throughout the system. But
Hey, Frank, can you move closer to the mic?
yeah, I'm sorry. Can I move the mic closer to me? Is that equally good? Sorry for being difficult. Yeah. So where were we? This whole probing concept, the ability to pay attention for the operators and all of the logic to pay attention to how much progress have we actually made through the computation, is sort of the key property that timely data flow introduces in the presence of streaming and iteration and a bunch of higher level notions of time that are more complicated than just what round are we on, or what's the current time with respect to wall clock. So yeah, okay, I said this already. Sorry. So what I thought I'd do next is show you just a little bit of a flavor of how you might write one of these operators. I mean, I put a bunch of stuff up that say things like filter and map and inspect and whatnot. The code is actually pretty pleasant. I think pretty pleasant to write these things. So, for example, yeah, okay, we like writing things like stream.map. That's really nice. Of course, you can write that. It's something that we've put into the core timely library. But you could also write this from scratch if you wanted to. I'm going to show you writing this operator from scratch. And at the same time, I'm going to pull out a bunch of really cool things about Rust that made this experience, I think, very pleasant and cool and saved a lot of headaches. So here's the same code written out in a sort of a little bit more like raw, timely stuff. There are a few fairly generic operators that you can write that describe the topology of the operator, in this case, unary. So one input, one output. With a few parameters, a sufficient number of parameters to describe the full behavior of the operator. And there are 3 parameters that get shown in this case. There's a requirement, first of all, about how data need to be moved coming into the operator. And for map, you might expect the data don't have to be in any particular place. Anyone can apply whatever piece of logic. So you don't actually have to shuffle the data to do something like a map. If you wanted to do distinct, for example, you would need to move the data, all the data that are the same, move them to the same worker so that worker can make sure there's only one copy. But in the case of map, the data don't even need to be moved anywhere. We want to give a tasteful name to the operator because otherwise it's really hard to tell these things apart. And then, yeah, finally we give it a closure. Essentially, we give it some logic which says, if I were to run you, if timely were to schedule this operator, what should it do? If I give you a handle to the input on which you can tug and get some data out, and a handle to the output at which you can push some data, what logic would you actually like to run? And I've written some here, which is actually the logic we use for map, and I'll talk you through it, especially for your benefit over here, because there's some very cool Rust idioms that show up that I take for granted at this point, but they're cool to just call attention to. So the code here is just taking the input and saying, as long as you've got data there for me, important, sort of keep pulling, and as long as there's still data there, a pair of a time and data, because all data have time associated with it. Well, what do I want to do? I want to take whatever data I receive and apply some logic, some transformation logic to it, and then send it. So let me prep an output session at this particular time, because I'm not changing the time at all in the map operator. We do that, and then we take the data and we drain it. This produces an iterator over the actual data elements. So data, as all of you know, if you're sort of anal grammatician, data is plural. Datum is the singular. So obviously I was talking about a set of data, not just one. The data are there. We go through each of them. And for each of them, we apply the logic, and we shove that into the session. That's the whole implementation of map. So let me call attention to a few cool Rust things. Again, some of you were like, okay, yeah, thanks, great. But first of all, like this whole wallet sum thing is I think, absolutely delightful, and I've totally taking it for granted now. But this is a destructuring which ensures that you only ever get to interact with valid data. And that's just really pleasant. There's no more testing of like, is this null or not? What is the data still valid? Has it been already? Have I seen it already? No, you only get to interact with data that the system has decided are valid, and it rules out a large class of errors that previously I had many of in C#, and I just don't have anymore. You don't have to worry about this type of thing. So this is nice. Elsewise you would have a whole bunch of tests saying like, is this null, is valid, all sorts of code that you just don't bother with anymore. We're using a closure in the middle. Logic is a closure. We're using it here, and delightfully, unlike a bunch of other systems, the closures happily result in specialization, this monomorphization that produces a new hunk of code each time we give a different batch of logic, which causes all of this to be inlined, which means if we had that map operator that just subtracted 1 from everything, it's not a virtual function call. It's just code that gets inlined and probably gets vectorized and goes really fast, because subtracting 1 from a bunch of things is pretty easy. It's delightful. It's the code that you actually would want to show up without the whole pain in the butt of manually unrolling the loop or putting horrible manual specialization in there, which I've also done in C#. Operators like drain transfer ownership. Now, Rust ownership is obviously a key important thing, and this is super useful in a data parallel processing environment where data movement and data-driven computation really cares about who's holding on to what piece of data, who actually is responsible for it, where when I hand it to you, what's the contract here, and ownership and move semantics just make this abundantly clear. Logic gets the piece of data in this case, and the signature of logic makes this 100% clear that when you write that code, you now own this resource. If it was a string that I was handing to you, you can do whatever you want with that string now. You can push characters onto it, make it lowercase, all the fun. I don't know what you do with a string, but and you can drop it at the end. And Rust is bright enough, of course, to know if you've just dropped it, it will collect all the resources for you afterwards. You don't have to worry about that. And this has always been a big pain with a lot of these data parallel systems. When you write this code, you might say, am I the only person who is going to look at data? I don't know if I should deallocate the resources at the moment, because there might be someone else who's going to see it. It's a disaster. There's no disaster here. It's nice. At the same time, data, the backing store for all these datums, ownership is not released by drain. It's retained. The system, in this case, gets to hold on to this resource and reuse it. And that's also very clear in all of the signatures, that you don't actually get to own data. And it makes my life very easy. As the system implementer, I get to reuse this buffer and not allocate stuff all over the place, which is great. There are a few more exotic things. In this case, the time that you get handed back is, in addition to telling you what the current timestamp looks like, maybe the round of data or the iteration, it's actually a capability, sort of an RIA-style capability. And as long as it exists, you're able to send data. This is something that Timely Dataflow is very interested in paying attention to, which is which operators out there might still send data. Right? This is sort of the fundamental thing it has to think about is, okay, you've written an operator. I saw that you received some messages. Are you going to produce any outputs? And the existence of this little the time object is what drives that. You have to hold on to one of those, and in order to produce outputs, you have to, in some sense, exert or demonstrate the capability in order to send data. But at that point, you can do a few things. You could throw it away, in which case the system will notice. you can stash it in a vector, and the system will also implicitly notice that you haven't actually released the capability yet. So it's a very pleasant, I don't know, it's a pattern that Rust makes very simple, and consequently makes the code a lot more pleasant and a lot less prone to error in our experience. There are a few other very clever things that go on in here. I had put them down, but I started to realize at some point they transitioned into anti-patterns. So I was going to stop talking about how clever I was with deref mute and stuff like that. But we can talk about that over substantially more beers than I have yet. Let me a few high-level points though about things about Rust that have made my life very convenient as a programmer. The clarity and resource management is absolutely a huge one. In building a big system, the things that have made systems like Spark, Hadoop, Naiad, even when we do them slow, was the resource management, the fact that, for example, you have a garbage collector that's constantly looking at your tens or hundreds of gigabytes of data saying, is it still valid? Who knows? I have no idea what's going on. Rust makes this very pleasant and clear, and it's just delightful. So, you collect resources at very obvious moments. You can reuse resources also at very obvious moments, and you end up with, again, fewer bugs than I had before. There's a lot of really nice compile time, I would say safety, both memory safety, but also control safety in a few ways. Programming patterns that you can enforce and cause people to write more likely to be correct programs. Fewer errors. Predictable performance was a really great thing. One of the reasons, again, that things like Naiad and other systems went slow was because you had this crazy garbage collector that would wake up and say, "Hey guys, I'm going to take 100 milliseconds now. Hope that's cool." And you have 100 computers, each of them doing this randomly. Is just a mess. The fewer errors thing is great. I have something, I don't know if this is something really to be proud of or not, but I've written this, I think, sort of cool distributed system. It runs over, it goes real fast, all these things. I don't even know how GDB works yet or LLDB works. I've not actually dropped into a debugger yet. There are bugs, for sure. Like, don't get me wrong, I've had bugs, but they've not been the class of bug that are, why does memory look like this? I have no idea what actually happened. They're mostly constrained to these logical bugs at the higher level. You can look at your code and you say, oh, yeah, okay, I see why that happens. So Rust has really ruled out, for me at least, this large class of bugs that were the real head scratchers that, this wasn't intended in any way, what happened? I don't worry about that class of bugs nearly as much anymore. The final thing, which I'm really pleased about, is when you fire up this sort of program, Rust, it's basically just there's not a lot of guff around. The whole zero-cost abstraction stuff is really great. We get to run your code, and not that much more than your code. And if you're confused about what's going on, you run it, you're like, oh, it's too slow, I'm annoyed. You can profile it, and it's like, yeah, well, it's your code, you wrote it. You want to change it, feel free. If you're computing too many hash codes, it's your fault. You can fix it. There's not a lot of crazy infrastructure in there that's boggling, that's hidden what you've written or that we've rewritten for you. Rust does a great job of taking hunks of code that you write and actually turning them into what runs, as opposed to rewriting what you've written into some other crazy language that you don't really understand. Or the mapping is really distant, and you can't figure out the sort of action at a distance between the symbols you typed and the code that you actually have executed on your computer. So there's some transition now in the talk to the next section. So I've given you some examples where you can write some crazy data flow graphs. I've said you can pretty much put whatever code you want in there, which is great. What should we actually put in there? Like, what's some examples? I'm going to show you now a slightly higher level language that is one of the things that you could write. I'm not saying it's the one you should write, and you shouldn't write anything else. Of course, you should write whatever makes you happy. But this is an example of something that's been written for you and might also make you happy. Or sleepy. We'll see. So this is sort of the differential data flow side of things, which I had like 5 different subtitles, and I couldn't really figure out the best one. But I went with real-time big data programming. I was just basically every buzzword I could find, and we're gonna put deep nets in there somewhere. And it's anyhow, it's not exactly wrong as you'll see, but still it's. It's buzzword bingo for sure. So our experience has been that people are pretty good at programming with collections or static things. They're good at writing a function that's like, oh, if you gave me a thing, I'll tell you how to act on this thing and do a few other things to it and give you an answer. They're a little less good at programming against things like streams or dynamic objects that change while you aren't looking at them or what have you. just in terms of getting correct programs out of people, it'd be good to restrict our attention. Well, we could helpfully restrict our attention to a slightly more static setting, or at least one where we control the dynamics that go on. So the idea that we're going to take here, and this is not a new idea, this is basically like SQL or something like that, but think about a collection-oriented programming language, one where you write a program that's as if you had one collection in front of you. You write that, and you say, that's what I want my computation to do. And that's delightful. We're sort of, but then we're going to go and totally change the collection underneath you, and we'll take care of that because we're responsible people. But your experience is approximately, you write a program, it maps some collection, some other collection. We're going to give you the sense that at any moment in time, the output that you're looking at is your program applied to the input at this particular time, as if we had just woken up, run your program on the input, and you get to see the output. Now, we're not going to actually execute it that way because that's horribly inefficient. We're going to do something a lot smarter, and the smarter thing here is to pull up timely data flow, basically, because that's really smart, and use some of these streams that we just talked about, where we have a notion of time. The records in there have some notion of time, and the records, instead of being data, are going to be little pairs of data and also an integer describing the change that's just happened. Like a record has been added, a record has been removed, like a +1 or a -1, no zeros. So we don't want to see any zeros there because that's not a change. So we'll think of these data sets instead of being big monolithic collections that we just see the same collection multiple times. We're going to show you the changes. Sorry, we're not going to show you anything. I apologize. We're going to show my operators and not your program. The changes that have happened to the collection. And we're going to take care of correcting your computation for you. The output are going to be similar. They're going to be streams, also pairs of data and changes, but describing the behavior of the changes in the output collection that's gone on. Telling you, yeah, okay, well, just a moment ago your collection was whatever it was, and it's just changed by these 5 records or these 10 records or what have you. Which is cool. It streams all the way down. That's really nice. It also means that they're nice and composable. So if your friend goes and writes something from sets of R to sets of Z, you can just stick them together, and it's all nice and composable. Yes, there's a question, and you have the.
Is there an implicit assumption that your prog is a pure function on D?
Okay. Yeah. Yes. Yeah. Sorry. You'll see the language as we get to it. It's definitely a very functional language, and that's going to be an important part of us correctly figuring out how to update your computation. So we're going to see a lot of things like maps and filters and joins and group bys and stuff like that.
So no side effects?
No side effects. I mean, you're welcome to put code in that causes side effects, but you should not be surprised when something will happen. Yeah. All right, let's look at an example. So this is a bit of code. This is going to be a graph processing example. So we have 2 collections initially. I've called them nodes and edges. So a set of nodes in your graph and a set of edges, which are going to be pairs of nodes. And the nodes are just some identifier and then true. We're going to do a reachability example, and the question is, can we actually reach a given node or not? And so we'll start with some people who are, yes, you can reach me. A bunch of edges that describe who's next to whom. And here's a little bit of code. I'm using things like join and concat and distinct, which I've just borrowed from relational algebra. But if I take the set of nodes and I join them with edges, meaning I go and I grab all of those edges that match something in the node set, I pull out their destination, and I concatenate that with the places I started from. I now have the set of these nodes that I can reach after one hop from the original node set, which is sort of, if this is like if you want to do a friends of friends type thing, this will tell you all of the folks who are within one hop of whomever you started with up in that nodes collection. It's a first step, so bear with me. But if you write this, you can then, to your heart's content, go and change the contents of nodes and edges. And as you add or remove things from edges, we'll receive updates to those nodes that were reachable after one hop from the original set of nodes. Maybe that's cool. Again, you can do this sort of thing today with incremental view maintenance in a SQL system. What you can't do is something that's cooler than this, which is to say, maybe we do that a few times, actually. Maybe, sorry, let's skip these stupid slides. Maybe we'll do that a few times. Maybe we'll take that little bit of logic that steps through and finds the immediate neighborhood, and we'll iterate it. And we're still thinking about collection-oriented programming. So we wrote a little body, like an inner loop body that says, starting from that set of nodes, let's repeatedly take whatever we can reach so far, hop it out one step, and do it a lot. In this case, we're gonna do till fixed point. Basically, we keep running it until it stops changing. Essentially, running it an infinite number of times, or use 64 max value. Nico, yeah. I'm happy to repeat it too if it's hard to get the mic over there. There's a weird box that you talk into.
Can I throw it? Yeah, you can throw it.
Oh, jeez.
One hand and a beat.
Nico just off camera was attacked.
So when you called .concat nodes, did you mean to call that, or did you mean to say reach? Like, it seems like you're adding in the always
very
the same
clever,
stuff?
yeah. So the observation is that if I had put concat reach in there, you'd be much more comfortable, right? Because reach was what I could reach just before, and that's obviously the thing I want to add in. I actually want to add nodes in, and if you write the math out, you realize that it all actually works out correctly because the set reach is not only the current frontier, but it's all of the frontiers, the sum of all of the frontiers of nodes that you've ever reached. So every time you take one step forward from that, you get the Gen 1, Gen 2, Gen 3, Gen whatever things, and you just need to add the Gen 0 nodes back in. That's a very good point. I shouldn't have caused troubles by putting nodes in there. This is actually a very helpful performance optimization to do, just to put nodes in there, because nodes changes less than reach changes. But then people ask questions when they, yeah. So both would work. Both would be correct. This one goes just a little bit faster, and I forgot to change it too. So that's the other reason. But this actually works. This is a cool thing that, and again, the thing that differential data flow does that, as far as I'm aware, no other system actually does today, which is it correctly updates the results of this iterative computation, even in the presence of removal. So if you go and remove an edge, even a very important edge maybe that made half the graph reachable, it will correctly update the computation, tell you about the changes that need to happen to your reachable set. Might take a little while if you remove a very important edge, but you'll get the correct answer, at least. So let's just, let's see. Oh, I'm sorry. Yeah, so this is good. This is the part where I tell you a few of the secrets and hopefully just overwhelm you with mathematical technology and no one asks any more silly questions. So the secret that's going on here, the secret sauce, inside this loop, the timestamps are a bit more exotic than they were before. There's not just a time for the timestamp, like a round of input. There's a pair of time and unsigned integer indicating the round of computation, which is very helpful. It allows us to tell the difference between changes that have happened because the input changed and changes that have happened because we've done a little bit more work. But it also drives the cool core of differential data flow, which is the way it does incremental computation. And the secret there is that all incremental computation, as far as I'm aware, prior to differential data flow, said, let's imagine a sequence of collections or whatever it is that we're talking about, where we'll talk about the difference between successive elements in this sequence. So, our variable changes from one thing to another thing to another. And then in a collection, this is pretty easy. We just take the difference between these two collections, and that's the diff at a particular time. This gets more interesting and a bit more mathematically vexing when we have something that's not a total order anymore. It's not a sequence. We have a partial order. In this case, we have pairs of integers, and it makes it a little bit more like a grid in terms of where things are. And you might ask, okay, well, what does that mean that, what should the diff at 5, 3 be? What do we take the diff with respect to? And the correct answer is not 5, 2. It's not 4, 3. It's something that's a bit more interesting. Though if you sort of take the analogy to differentiation and integration, you can figure out, okay, maybe it's got to be that thing that when I add everything up, it makes it integrate to the right thing, huh? And that has a technical name, which is Mobius inversion, because apparently mathematicians weren't cool with the whole you add things up right stuff. So Mobius inversion. Yeah. So other people have done reachability. There's a paper that's showing up in SIGMOD 2016. This has not yet come out yet, but it will be at SIGMOD in San Francisco in about a month. And you can go there. It's only $800 to go, which, as I'm told, is like a fraction of your rent anyhow. So it's in Berlin, this is 2 months' rent. So just think about that when you're thinking about where you want to travel next. They have cake too. Anyhow, sorry. So the big data log folks have gone and done some evaluation on graph reachability on a few data sets. They have more data sets, though. The two other ones they use are bigger. One of them I can't use because the license is weird, and the bigger one doesn't run on my laptop, and I feel bad. But so I evaluated the first two that they have. You might see that there's a few systems up there. GraphX has become the new sort of punching bag. There's 3 systems are from California: GraphX, Socialite, and Big Data Log. Myria is from Seattle, University of Washington, where I am also from, and you might notice that it's currently sort of cleaning up at the moment. It's going to change in a few slides, but another system that sort of cleans up is differential data flow running on my laptop on either 1 or 2 cores. And you can see that also does pretty well. And I don't really have a good explanation for this because it's shuffling around strictly more information than these existing systems are. They're all doing roughly the same thing, which is to say that we should learn about the set of newly reachable things, add them in, do whatever needs to be done after that fact. Differential, on the other hand, leaves you in a situation where you're able to actually do incremental updates. So what I'm going to show you next are some numbers related to me going and running the computations and then randomly ripping out nodes from the computation. So I'm just going to rip one node out at a time, do it 1,000 times, and report the average. And the numbers you see here are in the tens of microseconds range. So if you're looking for interactive computation, I don't know how quickly your graph changes. Maybe it's faster than that. That's fine. But you're in a state where you can actually do this sort of interactive computation and get real results real quickly. Yes, question?
How big is Orchid?
Yeah, none of these are very big. So the question is, how big is Orchid? I don't remember. The number of edges is larger than LiveJournal by a factor of 3, but the number of nodes is smaller by a factor of 2, and it's, they're in the hundreds of millions. It's not very exciting. You can run these things. So the main problem is that the graph that I would show you that's on the right of the screen is the Twitter graph. It has 1.5 billion edges, and that's a little bit more than my laptop can handle. It takes about 30 gigs of memory when you run differential. I only have 16. It's pretty close, and I have cheated repeatedly in the past to fit that comfortably in memory by doing some inappropriate optimizations. So I wish I had more exciting things to show you, or just a cluster sitting around. But I have an Amazon EC2 account, but I'm sort of loath to just spin up 100 machines in order to make a point. I'm happy to set people up with the code to do that, though, and try it out. When we were at ETH, we did a few of these sorts of runs. I have the numbers for Twitter for the next thing I'll show, connected components, while at ETH on a sort of beefy half terabyte RAM machine. The numbers basically are the same. I mean, they're pretty good.
The question is really how does the thing that you're doing, how do updates scale when there's size of the
Good question. So how does updates scale? And the answer I think here is actually really quite good. The updates do work proportional much more to the amount of changes that happen and the amount of work that you need to do. I think what it's sort of showing is that despite the fact that the number of edges tripled in Orchid, the updates didn't change wildly in terms of the amount of time that they take. They didn't triple in terms of the amount of work that they do there. You're going to eat a bit more if you have a much larger hunk of memory that you have to poke around in to find the correct answers. But in my experience, at least, the amount of work that you end up doing is largely proportional to the amount of change that actually happens. Depends on a lot of things, to be honest. It depends on how dense the graph is in this case, because if the graph is really dense, ripping out a node really doesn't change who can reach whom, because everyone's reachable already. If a graph is just very tenuously connected, ripping out nodes can make a massive change, and you see a very big number there, but it's a little hard to characterize.
So it's proportional to the amount of work that you have to do to get the update.
Absolutely proportional to the difference in the trace of the previous computation and the current computation, with some constants. Yeah, I have some pictures to show, and then I'll try to sort of wind down. Maybe I'll tease one other thing, but I just wanted to show you, if you actually run these things and look at, I did 1,000 random ripping outs of nodes and have the empirical complementary cumulative density function here, which is essentially out of the 1,000 samples, how long do each of them take? And you can see that a good fraction of them, 40%, basically do nothing. They don't change, the output does not change at all, and the system just takes about 3 microseconds to confirm that. It rips the node out, realizes, This wasn't an important set of edges for my computation. Guess we're done. Quite quickly. This is single-threaded at the moment. So these are basically the best possible numbers with respect to low latency stuff. Not the best possible numbers with respect to the right-hand side, though. Basically, the rest of them do something non-trivial, not wildly exotic. Typically, this is changing at about 10 nodes reachability and stuff such. That takes tens to maybe up to hundreds of microseconds. And then out of these 1,000, there was one sample that took more than a millisecond. It took 20 milliseconds, as it turns out. And this, if you look at what actually happened, the computation changed. Something, this is a fairly fundamental edge that got removed. And there's no magic here. There was a lot of work to redo. Some amount of work to redo. It went and it did all that stuff. So it's just like a little sanity check. We're not just accumulating numbers in a counter or something like that. The computation may have fundamentally changed. Someone needs to go into that work, and in this case, that was us. Just a few more pictures. This is 2 takes on the same computation where on the left-hand side we have single update at a time, and on the right-hand side we have thousands of updates at a time. Updates at a time, with both 1 worker and 2 workers to show you a bit on how the parallelism works here. And it's not too surprising. Like in the 1 update case where there's not a lot of work to do, the very low latency folks get pulled a bit to the right as we add more workers in, because you have a few people who are trying to work together on not very much work. They just trip over each other. But on the right-hand side, when there is quite a lot of work to do, there's basically a factor 2 improvement in the heavy volume case. So the throughput gets improved by a factor of 2, as you would sort of hope. And even that annoying 20 milliseconds thing gets cranked down to 10 milliseconds because the 2 workers happily collaborate. And you see the same sort of trend as you scale broader to more and more machines. As you add more workers, the throughput absolutely improves. The min latency does not improve as you add more workers. It's a sort of thing that the more people who get involved and have to coordinate, you eat a little bit more, though it's not as tragic as you might expect. But if you really want the fastest possible results, 1 worker is the right way to go. So let's see. I'll just lightly skip through a few more things. You can change the code a little bit if you're keen. Instead of circulating true everywhere, if each of these nodes send around a unique identifier, and then instead of taking a distinct, you do an argmin. So you say, wow, lots of people sent identifiers at me. Let me keep the smallest one I've heard of. You get a connected components algorithm. Basically, within each connected component, whatever the smallest label is in that component eventually spreads over the entire subgraph there. In a different connected component, hopefully there are different identifiers. Everyone in there gets a different thing. It's a way of computing connected components that's pretty similar in structure. And fortunately, these papers have evaluated them. You might notice that Miria here is no longer nearly as awesome as Big Data Log, but that's cool because I have Miria's back in this case. And again, we're seeing relatively good numbers on fairly simple deployment. Again, a laptop, not this laptop, that laptop.
You ready?
Bigger numbers in terms of the update latencies, hundreds of microseconds instead of tens. Yeah, shoot.
I was just wondering whether, given that these are relatively small data sets and they can fit inside a single laptop, is there any chance there's a kind of an unfair comparison, like by forcing 128 cores, you're forcing distribution on various other things? Oh, sure, but is it an equivalent comparison?
So you might say yes. They're self-inflicted numbers.
Okay.
The authors, they do have bigger data sets, and if I had access to the particular ETH machine that we had used, I would have given you a broader spectrum of numbers that went further out. I would say roughly the trend continues out to larger data sets. There's a little bit of a concern that the most compact differential can have in terms of an in-memory representation is a bit more expensive than the most compact that any of these systems could have. Though I believe that slop factor is more than made up for at the moment by the fact that Rust is relatively compact as compared to the JVM with respect to how it represents stuff on heap. Ariel. Yeah, so the question is, can we handle things larger than the memory of individual machines? And the answer is absolutely yes, because Rust does not shoot itself in the head when you pass physical memory. There are some points at which allocations do start to fail. So certainly if you're on Linux and you have an killer, your process is going to get shut down at some point because you told your system to do that. But you can spill to disk just fine. The internal data structures are largely written to support sequential access to main memory because that's fast. Has a nice property that when it spills to disk, it's also fast off of disk. So there's a bunch of internal design has really worked to make this work well off of external memory when possible. And whether it spills to disk or kills itself, it typically depends on how you've rigged your. I see. So the question is, if the data set doesn't fit in the memory of one machine, this is typically delightful. These models, the data parallel models will shard all of the data across all of the machines. So typically, for example, you'll take your graph, which has lots of edges, and you'll partition the edges maybe by a hash of the source vertex. So the 16 gigs of data get smeared all across your cluster, hopefully in a nice balanced way. The aggregate memory of the cluster is the more important quantity to worry about. Does my data set fit in the aggregate memory of the cluster? So typically the answer is yes, thumbs up. Sometimes if you have a crazy data set that has a lot of skew in it, there can be issues, but typically yes. Great. What was I saying? Okay, so delightful performance numbers. I think the programming model isn't particularly offensive. There's a lot of subjective qualities to. Do you like writing iterative computations this way? Maybe yes, maybe no. Other people, I gave a talk at Stanford, and one of the professors asked, do you really expect people to write stuff this way? And I said yes, and he walked out of the room. Opinions vary, apparently. But yeah, that's differential data flow. The next thing was abomination. I'm not really going to say anything about this because I think I'm. Is it okay? I don't want to. Okay, no, I'll keep going for sure. Sorry, as an academic, there's like a 55-minute timer in your head, at which point everyone just leaves the room. But no, let me walk through this. It's actually pretty simple, and it'll end on a nice note where all of you are very disappointed with me and and some liberties that I seem to have taken, and you'll be very suspicious of everything you've seen so far. So yeah, abomination. This is about serializing data. This is about you're writing programs in Rust. You have nice little Rust types that you thought were delightful, and you want to get them as quickly as possible to a big blob of binary and then back out again. So the name, abomination, you might notice, first of all, it's spelled incorrectly. That's not my fault. The name is the reaction that I got on IRC once I first explained what I was planning on doing. And someone, once they realized what was about to happen, announced in all caps, this is an abomination. With the remaining slides, go through with a little bit of skepticism. That's healthy. I'll point out a few places where I know that there are issues, and we can have a conversation about, are these really issues, or are these just like people worrying too much? And the answer is probably like, no, they're real issues. But yeah, no, I think I'll get some feedback. That's my guess. Can I have the box? I'm going to hold on to that. No. So the goal of abomination is to write the following two types of methods, an encode method and a decode method that operate on Rust types that implement some trait, abomination. So we're not going to do this for every type out there. We're going to do it for a few specific ones that we can get our heads around. But the two methods are going to, first off, take some type data, references some type data, and a place to put some bytes, mutable vector in this case. And the idea is going to be that somehow that type data ends up in the bytes. Yeah. On the flip side, we're going to do something which is a bit more suspicious. We're going to take some bytes coming in, mutable for some reason, and we're going to produce a reference to a T. So we're not actually going to produce an owned copy of T, just a reference, which might get a few people concerned. So you're like, well, what could that reference possibly point to, right? I mean, you can't allocate memory and then point to it because it's going to get deallocated at the end of it. So obviously it's going to point to the bytes that you pass in, and I guess some people are going to leave the room. But anyhow, so let's walk through how this might possibly work. If these were simple, if T was U64 or something like that, and you were using C++ and you didn't really care too much about safety and stuff, you might just use like memcopy, right? That's you might say, oh, cool. I've got an array of U64s. Why don't I just copy them into the bytes? That's awesome. And on the flip side, you might say, if you gave me a whole bunch of bytes and I'm supposed to interpret them as an array of U64s, yeah, that's cool. It's just a cast. I'll do that. That's not a problem. Doesn't exactly work with Rust, but we're going to make it work because because we like performance. So let's imagine I have some weird type, like a vec of pairs of I32s and strings. So in memory, they look like approximately. So a vec is a triple of a pointer, a length, and a capacity, which is telling us where does the thing start, how much of it is there, and how much more do we actually own. When we go look at that pointer, it's a whole bunch of I32 string pairs, which are somewhere in there an I32, some padding bytes, and then again a triple of a pointer length capacity, as many times as we have elements in the vector, and then each of those pointers point at some string stuff that is pretty exciting text data that we've put in. So a memcopy isn't exactly going to work here, but because we have the wonders of types, and we know that the first thing is a vec, and we know that vecs, their first field is a pointer, and it points to stuff that we could also memcopy, we can essentially write a heap crawler, which is going to walk through, and every time we get to a type that we know has some own data on the other end, we can go and follow it and copy it as well. And for each of the bits of type data that we then find on the other end, we can memcopy anything we need to there. And we basically just copy all the right bits that we need. Now, we're actually copying them as they are in memory. So we're copying a pointer, a length, and a capacity, a bunch of pointers. And it's a little crazy, right? Because the pointers are obviously junk. We can't keep them. We'll write them down for sure because that's fun. But if I hand this to another machine, pointers aren't valid. Even if I just serialize things and then walk away from my data for just a moment, the pointers might not be valid anymore. So I shouldn't treat them as valid in any way. So I've made them a different color. Yeah, in the back, question.
Why not encode them as an offset in the bytes array?
Why not encode them as an offset into the bytes array? Yeah, you could probably do that. We're going to do something very similar in just a moment. I mean, that's a totally same thing to do. I guess the point is here, that information already exists in the... Yeah, it might actually just do that, and that makes everything a bit simpler. What we're going to do is basically do that. I mean, we're going to reconstruct... we know where the data starts for each of these pointers, right? We're not going to do relative offsets because I don't think Rust is happy with relative offset pointers. They need to be absolute locations. So whenever we decide, cool, let's deserialize this thing, we're actually saying, well, where does bytes start? Let's add the right amount, the appropriate offset to that, because that's where the next bit of data is. We'll do that for each of the pointers, and then this is the bed. Then we'll just lie and say, let's pretend that's a vec of I32 and string. And you might say, well, that's ridiculous. But it's basically right. The thing that we point at actually looks like, there are a few caveats that are going to come up, but it basically looks like, if we pretend that it is in fact a reference to a vec I32, and we're like, well, we expect to find a triple there. Yeah, there's a triple, cool. We expect the first thing to be a pointer to somewhere in memory that if we follow it, looks like a whole bunch of I32 string pairs. That's right. And pretty much it's all good, actually, with a few caveats. It's very important that we're returning only a reference, right? Like if you try to interact with any of these objects in any mutable way, you're in deep doo-doo, right? If you try to extend the vec at all, you might try to deallocate the vector and you hand it back to Gemalloc, and it's going to freak out and you could get a panic at that point because that particular offset wasn't actually allocated by Gemalloc. Basically, you're in a world of hurt if you do anything other than just look at the data and pretend that it is what you saw. You're also in a world of hurt if you care about some other things. If you care about alignment, if you're on ARM, bad luck. x64 is fine with alignment screw-ups. Sorry? Absolutely. So you could do more work than I did. I agree. And there'll be, in just a moment, a few awesome places to go to contribute and stuff like that. No, it's a good point. There are a bunch of things you could do to try to make this a bit more robust, and it's a good question. Should those be things that are done? And if the answer is like, yeah, we should make this a bit better, I believe you, and it'd be cool to have some help. There are some other things which I'm not really sure about, like, according to the Rust documentation at the moment, anything you do with padding bytes is undefined behavior. It's not undefined behavior in LLVM. LLVM says it's just an undefined value. So, is reading and copying an undefined padding byte undefined behavior? I don't know.
Well, actually, the standard library uses memcopies
Mm-hmm.
to forms, and all of
So I don't think it should be a problem, but the documentation at the moment. Dan, do you have a question back there? Oh, I'm sorry. The comment was just standard library does that all the time, which I believe, though, if someone also said, surprise, Frank, I saw you did a mem copy of a padding byte and I've killed your program, the documents say that's okay. I don't really have a lot of leg to stand on here. There's a whole bunch of secret assumptions going on here that you're in the same architecture, endianness, word size, stuff like that. Really, you're in the same binary, because if you recompile the code and someone decides to lay out the fields even remotely differently, you're just, everything's bad. Though, in the setting that we're in, you're compiling one binary and handing it out to a bunch of computers which maybe have the same architecture because you rented them all from Amazon. And it can be pretty cool. It's worked fine with no issues for the past year. So I'm optimistic that it'll work for another week or two until someone's like, watch, no, there's no way, I'm going to kill it. But yeah, so let me put that out there. Okay, now all of you are like, oh geez, were the rest of his projects this bad? Oh shoot, there's a question. Yes.
Have you tried it on ARM?
No. It's gonna explode, right?
No, because ARM has unaligned reads now.
I thought so. Is this only like V8 and up or something like that?
You have to have a new ARM.
Okay. Yeah. Excellent. Good. I'm delighted that I can make even more inappropriate statements about how possibly this might work. Basically, what this is meant to show is that I'm not really sure. Like it works on my laptop. It works on the cluster computers I've used. It may work on more and more things as time goes on and people build more and more robust architectures. But if you go down to like a Raspberry Pi or something like that, maybe it blows up there. I have no idea. Sorry, it'll blow up on something. Okay. Yeah, good point. Sorry. One important thing here is that I've only implemented Abomination for a few types that I understood, and none of the wide types have I implemented Abomination for, and you're welcome to type that in if you want, but then it's on you. So I have just a few things to say before ending. This is just some performance stuff about Abomination. This is something that I stole from Eric. Where's Eric? He's behind there. So Eric does a lot of serialization stuff, and this is some code that I stole. This is a Cloudflare benchmark that I guess is originally a Go serialization benchmark, where they like to take this particular crazy data structure and serialize it a lot. Read it back and do whatever, a few different ways, then you get a sense for a quasi-realistic thing you might write to your log. How does that work? And you can sort of see whatever this log thing is. It's got a bunch of fields. Some of the fields are enums. Some of the fields are integers. Some of the fields are other crazy structs that have things like strings in them, and it has some strings of its own, and lots of gunk going on in there. So first off, this does not, as written, does not implement Abomination, so we can't use it. It's too bad, right? That's probably for the best. But if you're an adventurous person, you can type some very simple things. There are some nice macros that I have. Basically, structs are a lot like tuples, right? Struct has a bunch of things in it, and as long as each of the things implements Abomination, sort of tells us how do we chase its pointers, we can synthesize an implementation. I put unsafe in front of it because I don't know the right way to force a macro to be unsafe, but you have to type the word unsafe, and that makes it true. But you can sort of see this is us saying this log thing, it's got a few of its fields that need to be chased. They have own memory behind them. So when you're doing that heap crawler, make sure to go through those fields. HTTP and origin have some own things. These are the strings that you need to follow, and it will synthesize an implementation that goes and actually chases them. So that's cool. That's all you type. So let's see what happens if you're now Eric and you're like, cool, let's see how this works. Well, you can write this is Rust's delightful benchmarking infrastructure that is very simple to use. You just pull in this test crate and this bencher, and you write a little bit of code that says, what should I do over and over again a lot? And first we're going to say, what if we just make one of these new log items? So we go and we allocate a few strings and we stuff them into these fields. There are about 10 strings, and then we stuff them into these fields, and we make a new dealie. And we run that, and we see that takes about 267 nanoseconds to go and do these 10 allocations, fill them up with data, etc. This number is going to sort of serve as a frame of reference for are the other numbers we're seeing good or bad or whatever. Now imagine you're Eric and you want to serialize things. You put that Abomination implementation in already, so you can just call You just call encode whenever you want. And this code here is going to say, let's make a new log thing. Let's get some bytes ready. We'll encode it once so we can see how big it is. That's going to tell us a bit about the throughput in terms of bytes. But then we'll repeatedly just clear out this byte buffer, fill it up again with the encoded data, and do this black box thing, which makes sure that the optimizer doesn't optimize out the fact that bytes is important to keep around. And you get some cool numbers. This is, you sort of see that's 10 gigabytes a second. This is faster than any network that I think any of you have operates at. It's not technically, if you have 100 gigabit, you should talk. Yeah, how are you doing? It's quite fast. This is just one thread. On the serialization side of things, deserialization side of things, sorry. Code looks roughly the same. We're going to encode it once so that we have some valid bytes, and they're repeatedly called this decode thing. You might remember decode just goes and fixes some pointers. So it really doesn't do very much work at all, which gives you some really embarrassing deserialization numbers. So I mean, that's not a good number, right? It's nonsense. We haven't actually even touched all of the data in this case. But if you don't need to touch all the data, if you just wanted to go in there and look at one of the strings, you wouldn't have to pay for the cost of actually walking through all of the other strings you didn't bother with. There's a tweaked version of this that actually goes and deserializes it and tests that it's identical to the original one. So it does the derived equality test, and that is a bit more like 5 gigabytes a second deserialization. So it's still pretty good, even if you have to walk through the entire thing. Deserialization doesn't actually allocate an object; it just gives you a reference back. So if we wanted to reference, if we wanted an actual owned object, it would be a bit more expensive. Which I guess is the point of this is really fast, hooray! It's faster than this. So it's actually faster to serialize something to a big hunk of bytes and then look at it through the lens of deserialize than it is to make a second copy of it. So if you only need a read-only copy of data, which often we do in the big data settings, it's actually faster just to blot it down as bits and then hand it around as bits and pretend that it was actually valid data, because we don't have all of these different allocations we have to screw around with. The thing that we give up is, of course, the mutability, right? We can't take one of these strings and to lower it or to upper it or put a few more things on it. But we do get some pretty sweet performance when we need it. This is great for sending data around between bits of our computation, but it's also really nice. Differential data flow, for example, its internal state is essentially equivalent to an append-only log of the data it has received so far. So you could just keep this all memory if you want, or you could be a bit more clever and say, sweet, I'm going to serialize it actually, and then I'm going to drop it to disk, and I'm going to memory map it back in. And sort of nice lightweight fault tolerance there at the same time. It all just works out pretty nice because things are really fast, because Rust is great. The whole pile of code is about 400 lines of code. It's not even very complicated. You can look at it and be disappointed immediately without having to look very far. And that's basically it. I'm going to just have a few links up here, and these are the projects I've talked about so far. Basically, the pattern is you go to github.com/FrankMcSherry and just start clicking on things. And there are project pages there with descriptions of what's going on, documentation, stuff like that. There's a few other projects that maybe you're interested in, maybe not. Recycler is a sort of cool object pool. In the same spirit of Abomination, it sort of dives a little deeper into the structure of types and pools even nested resources, some columnar serialization. It's a cool blog. I don't know if you guys like reading blogs that say naughty things. Like all of these comments about performance numbers and stuff like that show up there. And raise some questions about, are we really doing the right work in large-scale computation at the moment, which maybe yes, maybe no. Usually I don't post a blog post about, yes, we're doing good stuff, because I have a black heart. And basically, it'd be great. I'd be delighted to have people either try these things out if they're interested in trying these sorts of things out because they have a burning passion to do big data stuff. If you have thoughts about things that are better, or just comments like, "Oh my God, this is a disaster. I mean, you should have done this way, this other thing," or even, "I just don't like what you did." Or if you like clicking on star things, you can go to each of these links. You can click on the star thing, and I will finally be able to overtake the Naiad project from Microsoft Research and retire and live in peace. But anyhow, that's that. I'm done. I thank all of you for your time coming out. And if you have questions, please grab me immediately after the talk. Or even right now while we still have a box. Where'd the box go? Sorry.
In the last benchmark you showed, the deserialization, the fast one, you kind of implied that you weren't doing the pointer rewriting as part of that?
So I meant to say we're only doing the pointer rewriting. So we're adjusting the pointers, but we're not even looking at the data the pointer points to.
Right.
So
you're touching the pointer bits, but none of the data bits.
Right. So all of those strings, for example, we don't traverse any of the string content. We just make sure the pointer points at the beginning of the string, which means we avoid touching a large amount of data that we have credited ourselves with having processed, which is partly why the number is a bit silly. But
do you touch the capacity as well of vectors and strings? I mean,
good point. So what actually happens in the code for like a vector, for example, is the pointer gets clobbered. It gets something to something that does not actually reveal the memory layout of your computer when you serialize it. The capacity gets set to the same thing as the length, which, in principle, Rust could happily say, I only have power of 2 capacities. That's ridiculous. Segfault. It's within its permit to do that. But yeah, that's basically what I do at the moment. The capacity is not kept at its original value because I'm a little concerned about what another person who's also typing unsafe, believing that they had a vector, might then do with the memory that they think that they... Because you have another copy of me sitting right next to it, like, ooh, I'm really clever also. Things go horribly wrong. Like the composability of unsafe regions of code is something that's very unclear to me. Or sorry, it's very clear. Don't do it. Yeah. Excellent. There's a question on the other side of the concrete. Yeah.
So I'm curious more towards the beginning of your talk and the timely stuff. You talked a little bit about data exchange and such, and I'm wondering, have you ever thought about trying to map this to a GPU in particular, where data movement is a little bit different there, and you would have to more explicitly control that?
So it's a good question. I'm going to defer you to other academic publications. I have other collaborators in the past, and nowadays there are a large volume of people who are trying to figure out how do we take these non-trivial models of computation. They're a bit more exciting than just doing matrix multiplication over and over again, but they're not quite general-purpose computation. One of the nice things about data flow, the reason data flow is sort of exciting, is you rip out a lot of the control flow potential, and it makes it a lot easier to do distributed execution. It also has the potential to make it useful on something like a GPU, where control flow is very scary. Though you have to be quite a bit more careful when you say, "Oh, I'll just add in a loop," or I'll add in this probe operator, which is actually the control flow part of timely data flow, and it's some exotic information that a GPU might have a hard time producing. The answer is no. I have not tried very hard, but it's the sort of thing that I think will be the subject of research going forward. People have looked at taking systems. In particular, there's a paper also at SOSP 2013 called Dandelion, which was about a data parallel system that they mapped onto a GPU that tried to look like a fairly general MapReduce style system, where the compute was pushed onto the GPU. They synthesized, they took C# bytecode and turned it into GPU ops and had that sort of thing actually running on the GPU. It's not clear that it's 100% win at the moment, but I think people are pushing on it, yeah.
Cool. So you've kind of shown a lot of numbers for like more graph-based incremental problems, and I'm wondering how does timely data flow or differential data flow perform compared to other solutions on like more batch kind of ETL type problems?
Mm-hmm. So I think there's a space of problems you might ask about, and let me try to be as candid and honest as I can. So a differential, for example, does absolutely disastrously on machine learning style workloads, where you basically take a bunch of data and you stir it together, and there isn't a lot of structure in terms of what influenced what. Everything just gets sort of put together in a big pile. It does work still quite well on a lot of relational OLAP style. So if you pull out benchmarks like TPC-H or TPC-DS, it still works quite well there because there's sort of tuple-oriented things still fit very nicely into the differential, the discrete data atoms moving around, interacting with a limited set of other data atoms. We've done limited experimentation with this. When we've done experiments, they've ended up working it well, but in part because I manually type in the query plan, so we don't have to worry about a bunch of levels of that stack. So the question is, can we get it to work as well as a well-tuned database? the answer seems to be yeah, almost as well. But in the case of differential, at least the special thing that it brings, which is different, is the introduction of iteration. So if you're looking at computations that involve iteration, you pretty quickly get to things like graphs, relations that speak of other relations in the data set. So it's sort of, we're looking at those examples because we want to show off what's new and interesting. And if you don't have that problem, it's a little hard for me to say, absolutely you should use differential because it's super important. You might just go with the thing that's better supported and has lots of documentation and it might not be in Rust, but grown-ups still use. Cool. All right. Well, thank you very much again. I'm not leaving yet, so feel free to grab me separately if you need. But otherwise, thanks. Here's Eric.
All right, thank you, everybody. There's still lots of cake left and pizza, so please enjoy the rest of the evening, and thanks for attending. Thank you, and I'll see you in a month. Goodbye.